this common emitter circuit to find what Vout will be given the fact that Vin is 2 millivolts. Okay? Now that 2 millivolt could be peak, it could be RMS, as long as we know it's an AC signal. Okay? All right, so how do we go about this? Well, that will require, for finding out Vout also will be an AC signal, is that we have gone through the AC analysis of this circuit. Prior to doing the AC analysis, we may have to do the DC analysis that is, so we can establish some baseline values that will be needed for our AC analysis. So mainly for a circuit like this, I would be concerned with what is the value of IE so I can figure out the internal resistance, RE prime. So let's go ahead and draw the equivalent circuit for this in AC. And then let's identify RE prime, and then let's figure it out. For this circuit to work in AC, we're going to have to reconfigure it as the AC sees it, or the AC signal sees the circuit. So anything that is VCC, for example, right here, will be considered ground. In other words, this point right here will be the same as this point as a reference. So that means R1 and R2 are in parallel. So we're going to move in this direction. So I'm going to move like this from left to right. Same thing here, from left to right, and evaluate the position of each element. And so if this is the base, for example, this whole line, okay, all of this is the base after the capacitor, we will try to see what, for example, this component looks like, what this component looks like, what does this component looks like, etc., as we move from left to right. So first of all, we're encountering this capacitor, right? I could draw a capacitor right here, but given a certain frequency f, we will assume that this capacitor's impedance will be almost zero. All right, this here is a coupling capacitor. So is this one. This allows us to connect to stages. So that means it allows us to this source to connect to the amplifier and the amplifier to connect to the load. But we don't want any of these two to have an effect in AC on the signal as it's processed through the circuit. So in other words, we want ZC here and this ZC here to be almost considered zero. Same thing here with the bypass capacitor, CE. We want its capacitance value, given a certain frequency F for the power supply, to also act as a short. So we have coupling capacitors, bypass capacitor, all will act simply like a straight line. So in other words, RE will be shorted in the AC model, right? So what's their purpose? And we've learned this before. In DC, you can consider the coupling capacitor as an isolating item that allows the DC currents to remain within here without going out back to the input or out to the output. So you can think of these as open switches as far as we're concerned in DC. In DC as well, this is a wide open, which means most of the current IE, all of the current IE that is, will go through RE in DC. And we're going to be doing that DC analysis in a minute. So let's go ahead and continue with the AC conversion of this circuit into the AC model. And we're going to use the pi model. So first, we're going to have R1 going to ground as well here. So this would be R1. This would be R2. And since we're going to use the pi model, so remember this here is still the base, we're going to have an internal resistance, right? Similar to the forward junction of the transistor, except since we're using the pi model, this would be beta RE prime. Okay? And again, so it's beta times RE prime. So we need to figure out what is RE prime. Beta will be given to us typically based on the transistor or the nature of this transistor from its spec sheet. Okay? And also, how did we set it up in DC? Because you might have a selection of betas or a range of betas that we would like to have here, for the circuit. We'll get to that in a minute. So next, we have a current generator. And guess what? This is beta IB. And IB will be the current that goes through here, through the base into the transistor. In other words, this is really IC. Notice these are all lowercase. Okay, so beta IB is beta times IB, that is. And so this would be ground as well. Now, what else is in parallel to it? Well, RC will be in parallel to that. So we'll have RC. What else? Well, think about this. This is also a short. So from here to ground, RL is in parallel with RC. And that would be RL. And let's get that point, since we're interested in V out here. We want to know what V out is at the end based on the value of V in, right? And keep in mind there is a relationship between V out and V in if this is an amplifier, right? So, and what would that be? Well, AV, or the amplification factor for this circuit, will be V out over V in. So in other words, if we do have AV, then this implies that V out will be equal to AV times V in. Now, we do know this. We don't know this one. So that is what we're going to be looking for to solve for this problem. And to do that, we're going to have to do some sort of an analysis to figure that out. And the way to do it is you could, look at this circuit here and try to figure out what is AV again. So AV is V out over V in, okay? And then we're going to write the equation for V out and the equation for V in and see if we can get this ratio again re-expressed based on the components that are on the circuit. That will be the trick behind this. Let's talk about V in first, right? So let's talk about V in itself. So what is V in going to be equal to? So as I said before, we're going to try to break each one of these terms into components that are in the circuit. Well, V in is the voltage from ground to this point. That is V in, from here to here. In other words, it's the same voltage against the internal resistance of the transistor. So in other words, this is V in as well. Aha! If that is the case, then this V in is equal to IB, so simply Ohm's law, times beta times little RE prime. Okay? All right, so again, we have this little RE prime because we're using the pi model. Okay? We could have used the T model, or we could have used the hybrid model. That would be a different exercise, each one of them, based on the same circuit. So, but the results will be pretty much the same. So, great. So we have V in. How about V out? Can we figure out V out here? All right, so let's look at V out. From here to here is V out. And we also know that we have a current IC, right? IC, going into this current source, right? Or in other words, beta IB, right? So and we're definitely going to use this beta IB to simplify things. But first, let's think about what's going on here. This IC going here is the sum of these two currents, whatever these two currents are. You can call this one IRC, IRL, if you add these two up, it will be IC. Well, I could look at it in another way. These two resistors are in parallel. And that's the common current to the total or the equivalent resistance going, so the current going through the equivalent resistance. So can I say that V out is IC times RC in parallel to RL? And the answer is absolutely, except you have to watch for one thing here. Notice the direction, the relative direction I picked for V out, right? So I'm acting as if this is a DC voltage here. So that means this is negative, positive, and this is just so I can have my bearing. If my current is in this direction and my voltage is in this direction, then they're not opposite to each other. So that means this is a negative value based on Kirchhoff. And based on Ohm's law, it still is IC times RC in parallel with RL. Okay, well, what else can V out be equal to? Well, that's minus beta times IB times RC in parallel with RL. Okay, now let's look at the ratio here. So let's go ahead and put the ratio together, and we'll do AV is going to be equal to minus beta times IB times RC in parallel with RL divided by, and that's Vn at the bottom of the denominator, IB times beta times RE prime. Now let's think about what's going on here. I have IB in the numerator, IB in the denominator, beta in the denominator, beta in the numerator. We can simplify these. So now AV will be equal to RC in parallel with RL divided by RE prime. Don't forget the minus. Okay, but here's the problem. We know this one, we know this one, we don't know this. As I said before, we're going to now do a DC analysis. So what we did here is called the AC analysis. Right? This allowed us to at least get to this point. Now let's go ahead and do the DC analysis. But we're not going to go ahead and figure out all sorts of currents and voltages. We have to be very selective as to what is it we need to do to be efficient. We really need to find what is the value of little RE prime. But we know from experimentation that this is 25 millivolt divided by IEQ, which means IE of operation, Q being the QS endpoint. Okay? So the trick to all of this is to find IE based on the DC analysis. Well, that's not that hard. Let's see why. Let's look at the circuit. What is IEQ? Well, that would be the current IE going through. So this would be IEQ. As Q means the transistor is in operation. That means everything is set up at the QS endpoint. That means I have a current IE going through RE. So that means I have a voltage VRE here, right? Going through, between this point, between the emitter and the ground. Okay, well, what else do I know? Well, I have a voltage VBE here. And that's approximately, this is DC, approximately 0.7 volts. And look at this point right here. From here to here, I also have a voltage. Or, even better yet, from here to here, I have a voltage. These two add up to VCC. But we're interested in this one. Since if we apply Kirchhoff right here, and we do a node analysis here, this total voltage will be equal to the sum of these two. Well, what is this one here? Well, if you think about it, here's VCC. Here's R1. And here's the base. Here's R2. Here's the ground. and we're going to the transistor, right? We have to take some assumptions here. And so VCC is the voltage from ground to here. And we're interested in this point here. Let's call it B. So that means the voltage against R2, we're going to call it VB. Okay? And we're going to assume, and most likely if you do the measurements, that the current IB here will be much, much smaller than the current going through IR2. In other words, IR2, or the current going through the resistance here, let me put it in capital because these are going to be DC. Let me capitalize these. These are DC values. IR2 is going to be almost equal to IR1. Okay, so that means the current going through here is almost the same as this one, which means, in other words, the current IB here is negligible compared to that current. Fine. Well, that tells us that VB then is simply a voltage divider. So VB is going to be equal to VCC times R2 divided by R1 plus R2. Okay, what can we do with that? Well, we also know, like I said before, this node analysis right here, that VB will be equal to VBE minus or plus VRE. Okay, so great. Can we find VB? Absolutely. This is known, this is known, this is known, and this is known. So all of these values we can find. And so what can we do? Well, we need to convert this now into something interesting where we can find IE. Because VRE is also equal to IEQ times RE. Okay? And we're interested in this. Okay? So what is VRE here as well? So VRE will be equal to VB minus VBE. Okay? And if that's the case, can I equate this with this? Sure. So can I say this is also equal to VB minus VBE? Yes. Which implies that IEQ is going to be equal to VB minus VBE divided by RE. Once I have that, because this is known, and this is known, I can go from there, plug it in here, find this, go back to here, and plug it in AV. Once we have that, then we can go right here, plug AV here, multiplied by VN, which we know is 2 millivolts, and you will get your V out.